you can see here we're going to use a sign substitution. That's the kind of the title. We're to evaluate the integral of the square root of 1 minus 4x squared all divided by x, with respect to x, of course. Now, here's kind of, let me point out to you this, that when we have the form square root of a squared minus u squared, then what we end up doing is replacing u with a times sine of theta, and then of course from there we can proceed further. Now I say that on the one hand. On the other hand, you know, in this case, see, in this case the u is actually 2x, isn't it? To have u squared be 4x squared, the u would have to be 2x. And so we can come in here and we can say, okay, well then 2x has to be a times sine of theta. Now, of course, well, what is a? Well, since we have a 1 in that first position, a squared is 1, so a itself has to be 1. So we have 1 times sine of theta. Now, that's the prescription on how to do it. If you will, that's more or less by formula. But what we have to recognize is eventually we're wanting to get a 1 minus sine squared theta, eventually, under the radical, because that can end up changing into the square root of just cosine squared theta, which we can deal with more easily, more readily. We can get rid of that square root. So we don't particularly have to go with this prescription necessarily. You know, we could just say, well, what does x need to be substituted with? So when we square it and we multiply it by 4, we get a 1. That matches that first term. And of course, x would have to be 1/2 sine theta. Because when we square 1/2 sine theta, we'll get 1/4 sine squared theta, and 4 times 1/4 is 1. Okay, I mean, I'm trying to explain to you, and it's hard to explain without pointing, that it's really what are we trying to accomplish. Now we're going to accomplish that by doing what I've shown over here. See, we're going to accomplish that by doing this. So here's the way we would approach this problem. If we didn't just think it out and we were trying to follow a prescription, the problem is I can't remember those formulas for very long. That's my problem. But we have a situation where the u would have to be 2x if 4x squared is supposed to be u squared, and the a would have to be 1 if a squared is supposed to be 1. Now, from the u being 2x, we're going to say u is, see, that's what we're doing, u is a times sine of theta. And so that means the 2x is a times sine of theta, which we saw a while ago is 1 times sine of theta. And so that tells us that x is going to be 1/2 sine of theta. Just divide both sides by 2. And that's what I was mentioning a moment ago, because now when we look at this integral, okay, we'll kind of block this off. When we look at this integral of the square root of 1 minus 4x squared, all divided by x with respect to x, when we make that substitution, I hope I'm going to have enough room. I'm afraid I'm squeezing myself again. When we make that substitution under the radical, we'll have the square root of 1 minus 4 and x squared. Let's go over here. When we square x, we actually get 1/4 sine squared theta. So we have a 1/4 sine squared theta right here. That's replacing x. And below, of course, we have x dx. And that really is ugly. I apologize. But the issue is under that radical now, when we multiply that 4 and that 1/4, we end up with just sine squared theta. Now, the issues yet are we still have to worry about replacing x, and we have to worry about replacing dx. Okay, so remember, x is 1/2 sine theta. So we can certainly take care of that. Let's kill two birds with one stone here. Under the radical, we have 1 minus sine squared theta. And the whole reason we've done this work is so that we could get a cosine squared theta under that radical. And there we can take the square root. Now, x in the denominator can be replaced with 1/2 sine of theta. That's what x is. Well, what about dx? Well, we use the information about what x is. See, if x is 1/2 sine theta, then dx is the derivative of sine of theta with respect to theta, or 1/2 sine of theta, which will be 1/2 cosine theta, won't it? 1/2 cosine theta d theta. So we can replace the dx out here with 1/2 times cosine theta d theta. Now we have everything in terms of thetas. Now when we take the next step, the square root of cosine squared theta is cosine theta. So we'll have a cosine theta times a cosine theta, so we'll end up with cosine squared theta in the numerator and sine theta in the denominator, and of course the 1/2s cancel, don't they? Okay, so with respect to theta. Now we have to deal with actually integrating that. And we have to be rather clever occasionally to do these things. What I'm going to do now is I'm going to, I don't see a quick way to integrate that. But if I change everything in terms of sine and sines, I may have a chance. So I'm going to replace cosine squared theta back to 1 minus sine squared theta, divided by, of course, sine of theta. Now the significance there, well, let's just write this down. Now we'll break that fraction into two parts. 1 over sine of theta minus sine squared theta over sine of theta, which is just sine of theta, isn't it? And of course, 1 over sine of theta is cosecant of theta. So we have the integral of cosecant of theta minus sine of theta with respect to theta. Now, we may have to go look this up, but the integral of cosecant theta is something that we're supposed to know. Whoops. When we integrate cosecant of theta, we get natural log of the absolute value of cosecant theta minus cotangent of theta. And of course, when we integrate sine of theta, we get negative cosine of theta. So we have a negative of negative cosine of theta, which is plus cosine of theta, plus our constant of integration. Well, we're not finished yet, okay? Because now we have to change things back to x's. And what we haven't done yet is we haven't done anything with our representative right triangle. So we come up with this right triangle. We'll let this angle represent theta. That's theta. And we need to name the sides based on the information of our substitutions. And we go way back up where we said 2x is equal to sine of theta. Okay, really then what we have is that the sine of theta is 2x. And since the sine function in right triangle is opposite over hypotenuse, we want to write this as a fraction 2x over 1, where 2x is the hypotenuse, the opposite side, and 1 is the hypotenuse. So we have a 1 here and a 2x here. Now, we would apply the Pythagorean theorem to find this side, and when we do, we would find out that it's the square root of 1 minus 4x squared. We're using the Pythagorean theorem to find that third side. Okay, well, what is all the stuff that we need? We need a cosine of theta, okay? Well, cosine of theta, see, I'm looking at our answer. We need a cosine of theta, don't we? Well, cosine of theta is adjacent over hypotenuse. And of course, the adjacent side is the square root of 1 minus 4x squared. And the hypotenuse is 1. So cosine of theta is just square root of 1 minus 4x squared, and we can make that substitution there. Now we also need cosecant of theta in here. Well, what's cosecant of theta? Well, cosecant of theta is the same as 1 over sine of theta. And sine of theta from above is 2x. So this is 1 over 2x is our cosecant of theta. Now, cotangent of theta, of course, is cosine of theta divided by sine of theta. And in this case, sine of theta is the square root of 1 minus 4x squared. And sine of theta is 2x. Remember, here's why we need cotangent of theta. It's right there. So, after we've used that information to be, now what we're going to do, of course, is we're going to make those appropriate replacements here. So we have, let me come over here, we have the natural log of cosecant of theta. Well, that's 1 over 2x. Minus cotangent of theta. Well, that's the fraction square root of 1 minus 4x squared divided by 2x. Plus, close absolute value, plus the cosine of theta, which is the square root of 1 minus 4x squared. And then, of course, plus our constant of integration out here. I guess one more thing that we could do is inside that natural log absolute value, we could actually combine those two fractions since they have a common denominator of 2x. So we could write this as the fraction 1 minus the square root of 1 minus 4x squared divided by 2x, close absolute value, plus the square root of 1 minus 4x squared plus our constant of integration. So we can do it by prescription, or we can do it by the idea of what we're trying to accomplish under the radical. We're trying to get a substitution so that we can convert under the radical to one trig function that's squared. And here it was to convert to cosine squared. And that's what you'll end up remembering in the long term, I suppose. We'll look at a tangent substitution on the next page. In this next example, we're going to investigate or use a tangent substitution. I'm kind of advertising, of course, what we're doing in advance, but we're to evaluate this integral. Evaluate the integral of 1 divided by the quantity 4 plus x squared raised to the power 3 halves. Of course, with respect to x. Now, let's just make a little note here, of course, so that we're not surprised that 4 plus x squared to the power 3 halves is equivalent to the square root of 4 plus x squared raised to the power 3. And that's the reason trig substitution would be very useful and needed in this case. So, as we think about how we're going to approach the problem, we're looking for a way to replace that 4 plus x squared with some trig combination that we can replace with a single term rather than two terms. The issue here is that we have two terms. So if we could, and you know, that leads us to think of 1 plus tangent squared theta, because 1 plus tangent squared theta can be turned into secant squared theta, and then we would have some hope. So I'm thinking to have a 1 plus tangent squared theta. Well, I don't really have a 1 there in front of that plus x squared. I have a 4. But if I had a 4 plus 4 tangent squared theta, then I would be in business, because then I could factor out that common factor of 4. So by prescription, this is what we're told to do, okay? Because of the scenario that we have here, let me write down what we're working on. The integral of 1 over 4 plus x squared to the power 3 halves with respect to x. Now, what's occurring to me is the plus sign has something to do with which I mean, that's what I'm looking at here, that plus sign in that denominator. That really gives me the hint on what I need to deal with, because I'm thinking that the only thing that has a plus sign, I mean, what are my choices? 1 minus sine squared x, or of course I could do a 1 minus cosine squared x if I have a minus, but that's a minus. We have 1 plus tangent squared x. Oh, well, that's a plus. And then we have secant squared x minus 1, which is a minus. So this is the only one that comes into mind. So that means I need to replace x with something. By prescription here, let me go back. By prescription, that is, we have an a squared plus a u squared. And so we understand that the a would have to be 2, since we have a 4, a squared would have to be 4, and our u would have to be x, because we have an x squared, and we need to write that as plus u squared. Now, what the problem tells us to do under these circumstances is name u as a times tangent of theta. That's what it tells us to do. And so in this case, that would tell us that u would have to be 2 tangent of theta. But after all, what is u? U is x, so that means x has to be 2 tangent of theta. And we could have figured this out without going through the trouble that we just went through. That is, we could have figured out, because we were dealing with the plus, we needed something plus tangent squared stuff. And we need the coefficients to be the same, and so we'd have to replace x with a 2 tangent theta, so when we square it, we get 4 tangent squared theta. Now, that's the bottom line. So what we're able to do then is that we're able to write, when we make this substitution, oh, I'm going to be crammed again, aren't I? We're able to write the integral of 1 over, and when we replace x with 2 tangent theta, when we place x with 2 tangent theta, we'll have a 4, but when we square x, we get 4 tangent squared theta. And of course, that's to the power 3 halves. And we still have a dx here that we have to deal with. Now, if you will allow me to bring this equal sign here, because I've run myself out of room, I keep doing that, don't I? Now, how are we going to replace dx? Well, we look up here at what x is. And remember, what we're really doing is we're finding the derivative of x with respect to theta. That's what we're really doing here. And when we do that, what do we get? What's the derivative of tangent? Oh, it's secant squared. And so what we've really done in the past is we've said, oh, well, dx is 2 secant squared theta d theta. So we always take the derivative and then end it with the variable, the d theta or the d whatever we're dealing with, dt, whatever. So now we have a replacement for dx. So our integral becomes the integral of 1 over, and let's do this at the same time. We can factor out the 4 from this expression, and when we do, we'll have 1 plus tangent squared theta left. But 1 plus tangent squared theta is secant squared theta over here, isn't it? It's secant squared theta. So this becomes 4 times secant squared theta, and that, of course, all is to the power 3 halves. And then our dx we're replacing with 2 secant squared theta d theta. So now everything is in terms of theta. Well, remember the way this is going to happen. Let's make another little note here, okay, as we're working, that 4 secant squared theta to the power 3 halves really means the square root of 4 secant squared theta, and that square root raised to the power 3. Well, of course, the square root of 4 secant squared theta is going to be 2 secant theta, and that's raised to the power 3. And of course, that gives us what, an 8 secant cubed theta. So in the denominator of this integrand, that all simplifies to 8 secant cubed theta. And we're multiplying with a 2 secant squared theta, d theta, and you can see that we have some simplification that can occur here. We have a 2 over 8, which is 1/4. Let's go ahead and factor that outside the integral. And we have a secant squared over a secant cubed, so that's going to be 1 over secant of theta d theta. Now, 1 over secant of theta is just cosine of theta. I mean, secant of theta is the reciprocal of cosine of theta, isn't it? So this is really 1/4 times the integral of cosine of theta d theta. Well, now we feel pretty good that we can complete our integral. That'll be 1/4 times the integral of cosine, of course, is sine, plus our constant of integration. But we're not finished, because we need to change this back into thetas, into x's. Now here's where we started. X is equal to 2 tangent of theta, which means tangent of theta is x over 2. Okay, and remember, tangent is opposite over adjacent. So if we're setting up a right triangle, and we call this angle theta, the tangent of theta is x over 2, so that would mean this side would have to be an x opposite over adjacent. And when we use the Pythagorean theorem, then we would calculate that the hypotenuse is the square root. We calculate as the square root of x squared plus 4, okay, is what we'd actually calculate probably, which is the same as the square root of 4 plus x squared, isn't it? Okay. So in fact, I'm going to call it that because that's probably what we would see as a result somewhere. And that's because our original had a 4 plus x squared factor in the denominator, if you will. So when we're calculating now, when we're replacing sine of theta is opposite over hypotenuse. So we would have replacement for sine of theta. Opposite side of theta is x, and the hypotenuse is the square root of x squared plus 4 or 4 plus x squared, however we decide to write it. And we're writing it this way, plus our constant of integration. And then, of course, we can take one more step and write this as x over 4 times the square root of 4 plus x squared, plus our constant of integration. Okay, well, next we'll go through the process, just to be complete, of dealing with a secant substitution. We had a sine substitution, a tangent substitution, and so next we'll have a secant substitution, and then we'll do a few extra pieces, look at some maybe calculating, we'll look at some special situations that deal with all of this. So as you see here, we're going to use a secant substitution. And of course, that's a big hint right in the beginning. But we have the form, of course, the square root of u squared, the variable expression, minus a squared, the constant expression. And the reason we know that we're going to use a secant substitution is because the variable part, okay, if we replace u with something about secant, let's just do this right now. And in fact, we can get an a squared in this position as well, minus an a squared in the second position. Then the whole idea is that we'll have under the radical an a squared times a secant squared theta minus 1. And the significance of that is that this is tangent squared theta. So we'll be able to actually take the square root. So that's the idea behind what we're going to do. Now, this one's a little more involved than what we've done before. Let's kind of stretch this on for the rest of what we're doing. By prescription, it tells us, well, in this case, we know that u is going to have to be a 5x, right? So, because when we square it, we've got to get 25x squared. And we know that a has to be a 2 because we have a 4, and a squared is 4. And it's of the form variable expression minus constant expression squared. Now, the substitution that we're supposed to use here, and we'll see why this works, okay? The substitution we're supposed to use is that we're supposed to let u be a times secant of theta. And you see why that we were doing that from above. That's the reason we were doing that. Well, in this case, u is really 5x, isn't it? And in this case, a is really a 2. So we're supposed to replace a 5x with 2 times secant of theta. That's what we're supposed to do. Now, I guess we don't really see a 5x up there. I mean, we could do this. Really what we want to know is, how do we replace x? That's really what we're wanting to do. Or we could just say this, that we could replace 25x squared. See, if we square this left side, that would be squaring the right side, which is 4 secant squared theta. So we could replace the 25x squared we see under the radical with 4 secant squared theta. And that's really the secret to what we're trying to accomplish here. So we come down to evaluate this integral. So what we're going to first do is we're going to replace, just as I said, the 25x squared with 4 secant squared theta based on what we've done right here. 4 secant squared theta, and then minus 4 is still under the square root, and an x dx. Now, obviously, we've got to deal with that x, and we've got to deal with that dx. So, the fact that we have 5x, how are we going to deal with x? Well, the fact that we have 5x is 2 secant theta, then x would certainly be 2/5 times secant of theta. So we can put a 2/5 secant theta in the denominator for our x. What was it? 2/5 secant theta. Now what about our dx? Well, the way we'll calculate dx is we'll look at our value for x here. Since x is 2/5 secant theta, dx is the derivative of 2/5 secant theta with respect to theta, then times a d theta. Well, of course, the derivative of secant theta is secant theta tangent theta. So dx is 2/5 secant theta tangent theta d theta. So that's what we're going to put here in the place of dx. We have a 2/5 times a secant theta tangent theta d theta. Now, let's take care of that square root. Let's take care of that radical. Because we already know that we're going to factor out of 4 from that expression under the radical. And when we do, we'll have 4 times the quantity secant squared theta minus 1. But the secant squared theta minus 1 is really a tangent squared theta. So what we end up with under that radical is 4 tangent squared theta. Well, the square root of 4 tangent squared theta is 2 tangent of theta. So that's how that simplifies. And in the denominator, well, let's look here. We're going to have this 2/5 that would be in the numerator otherwise, and the 2/5 in the denominator that we can cancel. And we'll have the secant of theta that we can cancel in both places. So we're really just going to have an over 1 here and left with a tangent of theta, d theta. Well, let's see what we can do next. Of course, that's really the integral. We'll factor out the 2. That's nothing more than the integral of tangent squared theta d theta. Now, of course, that presents some roadblocks, but we've been through this section on how we deal with powers of tangent, of secant, and so on. And in this case, I think if you'll look back at what we did before, but regardless, with this case, we could change tangent squared theta into a secant squared theta minus 1. Now, the reason I would want to do that is I know how to integrate secant squared theta, and I know how to integrate 1. And so this makes our life much easier for us to complete then. Remember, the integral of secant squared theta is just tangent theta. Minus the integral of 1 with respect to theta, of course, is just theta. And then plus our constant of integration. Now, what's left for us is to set up our right triangle that represents our situation here, okay? And so our right triangle would look like this. Here's our theta. Now, what we started with, here's what we started with. That 5x is equal to the secant theta. So that really tells us that the secant, well, let's just leave it that way for right now. Excuse me, 2 secant of theta, my bad. So that really tells us when we solve for secant of theta, we divide both sides by 2, we get secant of theta is 5x divided by 2. Now, secant of theta, let's write this down. Secant of theta is nothing more than 1 over cosine of theta. And so it's a little easier for me to deal with cosine of theta than secant of theta. So cosine of theta is the reciprocal of secant of theta, so it's 2 over 5x. Now, the way we calculate cosine in a right triangle is adjacent over hypotenuse. So we're going to make the adjacent side 2 and the hypotenuse side 5x. And then we're going to use the Pythagorean theorem, okay, just as I've talked about before, you know, to remind you, just so in case we kind of forget, that the Pythagorean theorem tells us that the sum of the squares of the legs is equal to the square of the hypotenuse. So if I'm thinking of this as side B, and of course this would have been side A, and this, of course, the hypotenuse is 5x. So that tells us if we take A and square it, plus B squared is equal to C squared, well, C being 5x, so that gives us 4 plus B squared is equal to 25x squared, or B squared is equal to 25x squared minus 4, but of course B is a side, so it's not going to have a negative value of B, so B is the square root, it's just the Pythagorean theorem, of 25x squared minus 4. Now that's what I've been doing all along, I just haven't gone through the steps, so I thought maybe I ought to do that at least one time. So this opposite side is the square root of 25x squared minus 4. Okay, well, here we go then. We're going to replace tangent of theta. What is tangent of theta? Well, tangent of theta is opposite over adjacent. So in this case, the opposite side is the square root of 25x squared minus 4, and the adjacent side is 2. And then we have minus theta. Now this may be the most difficult part of this situation. So let me remind you here, and I've kind of run out of space on the left side, so let me come down here at the bottom right now. Okay, this is all stuff that we're using to figure out what we were doing, isn't it? Okay. We've got to solve for theta. Now, one of the things that we know about, let's look over here at cosine of theta. See right here. Let's look at this cosine of theta. Since cosine of theta is equal to 2 over 5x, then the inverse cosine of 2 over 5x is the angle that we need to take the cosine of to get 2 over 5x. So inverse cosine of 2 over 5x is actually equal to theta, isn't it? That's what we need to be concerned with here. So, in this position in place of theta, we're going to put inverse cosine, sometimes it's called arc cosine. Remember, that could also be referred to as arc cosine. It's the same thing, it's just different notation. But I'm using inverse notation here. Inverse cosine of 2 over 5x is what theta is. That's even hard for me to read. Plus our constant of integration. And then we could actually distribute that outside factor of 2. So when we multiply 2 times that fraction, in the first position, we end up just getting the square root of 25x squared minus 4 minus 2 times the inverse cosine of 2 over 5x, a little neater, plus our constant of integration. So we've looked at an example of each of the types of substitutions. Next we'll go into, I wouldn't call it a word problem, but a problem where we're going to find the length of a curve, the arc length.